Hello, Mr. Munyon here with 19-1, the right triangle altitude theorem. So in this activity, we are going to be focusing on learning about the relationship when an altitude is drawn on a right triangle from the right angle to the hypotenuse. So like the example down here, we have a big right triangle MAE. There's a big right angle there. And then if we draw the altitude from that right angle to the hypotenuse, we're going to learn what properties these triangles have. So given the figure, we have the big triangle where AN is perpendicular to ME. That's already labeled for us. And the measure of angle M is 70 degrees. So this angle right here is 70 degrees. Let's go ahead and see if we can determine these other angles as well. So the measure MAN, so MAN is this angle here. And because this is a 90-degree angle, a linear pair, the other side has to be perpendicular as well, so it's 90. So the triangle sum theorem, 180 minus 90 minus 70, there's 20 degrees left for this angle here. All right, so MAN is 20 degrees. All right, what about the measure of angle EAN? So EAN would be the other side. These two together are adjacent and they make a 90-degree angle, so they're complementary. So this angle here has to be 70 degrees because those are complementary. 20 plus 70 does equal 90. And the last one, angle E, I see down here by itself. I can see either on the big triangle or the medium one. Either way, doesn't matter. 90, 70, this last angle here has to be 20 degrees. So now that I know all of the angles on all three of the triangles, there's a big triangle and then a little triangle on the left and a medium-sized triangle on the right, I could write a similarity statement between the triangles that have angle-angle similarity. So MAN, the one on the left, and triangle AEN, the one on the right, both have a 90-degree angle, a 70-degree angle, and a 20-degree angle. So we only actually need two of them to prove that they are similar to each other using angle-angle similarity. Also, the bigger triangle also has a 90, a 70, and a 20-degree angle. So it is also similar. So all three of these are actually similar. So MAN is similar to triangle AEN, which we already listed. And it's also similar to the big one MAE that we had up there, the big triangle. So similar to triangle MAE as well. All right, so name the type of special segment AN is in relation to MAE. So AN is an altitude. It goes from a vertex and is perpendicular to the opposite side. So it is an altitude. And let's do Pythagorean theorem. It says given AN equals 9 and NE equals 12. So AN is 9 and NE equals 12. So if we did Pythagorean theorem, we could do a squared plus b squared. That's 9 squared plus 12 squared equals AE, or the hypotenuse of that one, squared. Oops, that's 144. Take the square root and we get AE equals 15, which makes sense. That is just a multiple of a 3, 4, 5 triangle on there as well. So that one does make sense on there. So AE is 15. Now it says use properties of similar triangles to see if we could figure out some of the other pieces on this one. So we did Pythagorean theorem to figure out this one, but how would we go about figuring out any of the other pieces? So like if I know all three sides of this triangle, look at the little triangle here. Let's call this X for now, just to have a name for it. I could say the short leg of the little triangle corresponds to the short leg of the medium-sized triangle. Notice on triangle ANE, 9 is the short leg. So I could write a ratio of corresponding sides of the short legs. that should be equal of a ratio of corresponding sides of the long legs of those same two triangles. So on MAN, 9 is the long leg, and on the medium-sized triangle, 12 is the long leg. So I could multiply both sides by 9. And we get 6 and 9/12, or 6 and 3/4. All right, so for x, or mn, would be 6 and 3/4, or 6.75. And then to solve for the last piece, am, we could just do Pythagorean theorem again. Is that the last one? Ma? Yeah. So notice now that I know this is 6 and 3/4. We could do Pythagorean theorem again. We're not going to actually do the Pythagorean theorem because we know how to do that, but we would get 11.25 if we did do Pythagorean theorem there. We could have also done Pythagorean theorem using this hypotenuse here, this leg, and this piece, and we'd get the same answer, 11 1/4, or 11.25. So for that last one, 11.25. So basically, given, just a little information here, like two pieces, two sides of one triangle, we could use some combination of similar figures and Pythagorean theorem to help us figure out the rest of the pieces of this triangle. So basically, if you have an altitude of a right triangle and you know a couple of pieces, you can set up proportional ratios, or you could set up Pythagorean theorem and solve for most of the rest of the unknown pieces there. All right, so as I mentioned, we're not going to do the proof, but we do need to know the theorem that says when you draw an altitude on a right triangle from the right angle to the hypotenuse, you get 3 similar triangles. And that's always going to be the case because you're going to have angles that overlap with the big triangle that create angle-angle similarity. All of your triangles will have at least one right angle, and each of the 2 smaller triangles have at least one overlapping angle with the big triangle. So it always creates angle-angle similarity, proving that we have similar triangles. All right, so as I mentioned, we're not going to do that proof. So check your understanding. See if you can redraw all these similar triangles, but orient them where the right angle is in the lower left position. So you can draw a big one, a medium one, and a small one, and see if you can correctly label the vertices. Like I know that C on the big one is going to be right here, and I need to label the other 2 pieces as well. So pause here, try it, make sure that you can do it, and then I'll have the answer here in just a second. All right, hopefully you tried these on your own, because this is an important part of being able to set these up and solve for your unknown pieces of similar triangles using proportions, is actually being able to draw them like this. That way you can very easily identify which pieces are corresponding. If you know 3 out of the 4 pieces you could plug into a proportion, like, hey, these pieces here correspond and these pieces here, and I could solve for x. X over BC equals CD over CA. So check your work. Make sure you identified correctly the vertices for the large, medium, and small triangles. All right, moving on to the practice. It says in figure triangle XYZ, it's a right triangle, and YW is an altitude. Perfect. Suppose that we know that the measure of angle X is 62 degrees. And what other angle in the figure must also be 62 degrees? If I start with the smallest triangle, I do know that I have 90. I have this 62 degree angle, and on a triangle has to add up to 180. So 180 minus 90 minus 62 gives me this is 28. And then these have to be complementary here. They have to add up to 90 and that right angle at Y. So 90 minus 28 is 62. So this angle here, I shouldn't put the same number of arc marks there. So this angle here now has to be 62 as well. So we could say angle WYZ has to be 62 degrees. You could have used the triangle sum theorem here to figure out z, and then done it again to figure out y. Done the big triangle to figure out z, and then the medium triangle to figure out y. So a couple of different ways that we could do that problem. On 9. All right, given the figure is a right triangle with an altitude drawn, the measure of angle E is 25 degrees. So E, we have 25 degrees. DF is 8, and DE is 17. So the entire side over here is 17, from D all the way to E. All right, complete the similarity statement. So first thing, I want to make sure that I can identify what is congruent, what is similar to the big triangle DEF. All right, I'm going to redraw all of my triangles, just like I did on the first one, where the right angle's in the bottom left, because this one's kind of already drawn like that. All right, so the big triangle is easy because it kind of looks like the one I drew already. D goes up here, F, and E. But the other ones are a little bit trickier. How do I know how to actually label the vertices on the medium one? Well, one way to do this is to identify the actual pieces. If I wanted to use the angles, that's probably the easiest way to do it. Every triangle has a right angle, a 25-degree angle with one arc mark, and then a 65-degree angle with 2 arc marks. So this one will be 1 here and 2 here. So then my big triangle will have 2 here, 1 here. All of my triangles should have 2 here, 1 here, 2 here, 1 here. So this actually will help to label the other triangles. So on the medium-sized triangle, the 90-degree angle is at G. The angle with 2 arcs is at F. And the angle with 1 arc, the 25-degree angle, is E. On the little triangle, my right angle is at G. My angle with 2 arcs is at D. And my angle with 1 arc is at F. Okay, so then label any pieces that we know. So right here, 8 is the small side of the big triangle. So that piece should be 8 on there. The big leg right here is 17, so I can label that one as 17 as well. And this 8 is also a piece of the small triangle. That's the hypotenuse of the small triangle. So notice right here, the hypotenuse DF should be labeled DF, should be 8 as well. Okay, so I can write my similarity statement. DEF is similar to FEG. In same order, DFG is the smallest one. And redrawing these is by far the easiest way to do these to identify which pieces correspond. And it also helps us visually see for the next problem, number 10, which pieces we can use to set up a triangle proportionality theorem. So number 10 says measure of angle D. Well, let's go ahead and label any angle with 2 arcs is going to be 65 degrees. And any with 1 is 25 degrees. So D is going to be 65 degrees. DFG, so DFG is a 25-degree angle. GFE, so GFE is 65. So side FE and FG. So FE, how can I solve that one? Looks like just Pythagorean theorem I can use on that one. All right, so we're solving for a leg, not the hypotenuse, so I'm going to subtract on this one. So 17 squared minus 8 squared. 17 squared is 289, minus 64 is square root of 225, which does equal 15. So FE is going to equal 15. And if I wanted to solve for FG, how could I go about doing that one? Oh, I guess I know FE now is 15. All right. I see here that I have FG is what I'm looking for, and FG corresponds to 8. So that is a pair of corresponding sides. I can write a ratio. And on similar triangles, or any similar figures, you should be able to write a ratio of corresponding sides. X corresponds to 8. 15 corresponds to 17. So I could set up a proportion x over 8 equals 15 over 17 and solve for x. So if I multiply both sides by 8 and then plug that in my calculator, 7 and 1/17. So a little bit more than 7, so like 7.05. If we rounded there. Okay, so we used both Pythagorean theorem to solve for this side, and we set up a proportion, x over 8 equals 15 over 17, which I mentioned is exactly what we're going to use on these types of problems. All right, for 11, it does say investigate pretend we have an isosceles right triangle here, and then do a proof. We're not going to do the proof, but we are going to draw a quick altitude and notice what happens right here. As soon as you have an isosceles triangle to start with, when you draw the altitude, the other two triangles are going to be similar. They're going to be isosceles right triangles. So even without knowing exactly how the angles show up there, if the biggest triangle is an isosceles right, any smaller triangles are going to be isosceles right triangles. That concludes our lesson for here. We're going to learn a little shortcut, and if the shortcut doesn't make sense to you, don't worry, this is our backup plan. If you feel good with similar figures, you know how to do Pythagorean theorem and solve for sides using proportions, you'll be okay.